All right. Thanks, Mooney, for warming up the crowd. And thanks, DBT, for pulling us all together. I was joking with Claire that filling this room is easy because I know that if you just gauge the temperature on DBT on the Slack, how excited everybody is to interact with each other and talk about this new tool that we've all found relatively recently, and how fun it is to talk about how we're using it. So I started the data team at Bowery about a year and a half ago, almost exactly when I learned about DBT, and so built sort of our world from scratch with DBT in the middle. So this story is about one particular aspect, but anything you asked me about Bowery and data would be about DBT.
Where did you work before Bowery?
I received most of my formal training in data from John Mooney here at Betterment. So I worked, I was in academia and left academia, came to Betterment 5 years ago, worked here for about 3 years as the first and only data scientist, and built out those ideas, and then left it in Mooney's stable control. So now I do indoor farming. What is indoor modern farming? So when we say modern farming, modern is obviously a great way to describe any business, but we specifically mean indoor. So we grow not in greenhouses, not out in a field, but specifically in a completely closed and controlled environment. Hydroponic, so our plants don't grow in soil, they grow in water that flows constantly and provides them with the nutrients that they need. LED lit, so I said already that we're not a greenhouse, but we don't have natural light. We don't structure our buildings and build our grow system, or we do build our design our grow system to take advantage of the amazing efficiency of LED lighting, which has really changed this opportunity in the last 5 years to make this an energy and cost efficient business. Vertical, one of our goals is to bring fresh produce production close to where it's consumed, which means that space is a valuable commodity. We want to be as tight into population centers as we can, which means that one of the advantages we can have over traditional farming is going vertical. So we'll have crops growing all the way from the floor to the ceiling in large warehouse spaces. And the third piece is automated. We want to make as much of this process scalable, right, and driven by technology. So that means automating the movement of crops around through the farm like a warehouse, the processing, the packing, all of these things, the management that people do of crops traditionally by walking through the fields. These are all things that we can do more efficiently, more automated with technology. And what does that get us? Those are all sort of fun technology claims, but they are not valuable to the consumer. What it does for the consumer is that we grow entirely without pesticides or any sort of treatments or pest prevention because we're inside. We don't have any pests, and so we don't have to do any of that. We don't have to put any of that in the environment or in your food. We grow our produce with 95% less water than it takes to grow the same produce out in a field because all the water that we bring into the building stays in the building. And so it gets consumed by the plants, it gets transpired by the plants and collected and put back into the system. The only water that leaves is the water that we spill from time to time because nobody's perfect, and the water that leaves in the cells of the plants and that you eat when you bring it home. And last, transportation. A huge amount of the total energy consumption in traditional agriculture is spent trucking your lettuce in December to New York from California, right? So not only is it 3 weeks old when you're eating it, it has spent the last 3 weeks on trucks moving all the way across the country through this really heavy supply chain. So modern farming means using those technologies to solve those problems so that we all get to eat fresh, healthy, clean, local produce year-round more productively than we could traditionally. Bowery as a company just turned 4 years old recently. We're Series B in terms of sort of development. We're almost exactly 100 employees. I think our all hands yesterday, we said we were 99, but 3 people were starting soon. And you can buy arugula, kale, lettuce, basil, bok choy, cilantro, parsley, and some blends of those at any of these places. So some Manhattan hip grocers, some of the biggest grocers in the country that you're familiar with, all of their online arms, as well as some restaurants in the New York area. Right now, we are only in the New York area. We are under construction on our first farm in another city. And before you know it, we'll be everywhere. So tell your far-flung friends and family. So that's all fun. But we all here care about the data aspect of whatever business we're involved in. And so data at Bowery means a few different kinds of ways to improve and facilitate this process. Constrained operation or optimization in the operational aspect means that we're running a production facility. We're running a warehouse of sorts, a warehouse that happens to be growing thousands of crops at the same time. And so we have a lot of problems trying to decide where to put every crop, how to move every crop, when to do which work so that it's most efficient. And so those are all data and AI team problems, how to move things around, how to use all of our resources most efficiently and to maximize that productive capacity of the farm. Scaling the green thumb means computers don't know that much about gardening, and we have a lot of people who do know a lot about it, but the problem is they can't go everywhere through this farm and do walkthroughs and check on and build a personal impression of how everybody's doing all the time. And so we need to scale that. And so how we scale that is by structuring the data about how all of our crops are doing, what they've experienced, and bringing the things that need human attention to the view of those humans who have those skills. And so our job is to figure out what's important, try to recognize things that require some sort of intervention or some sort of attention, figure out what the right prioritization is, and then surface that to the people who can, rescue an arugula crop before it gets too unhappy. And then finally, finding the perfect recipe. So one of the sort of grand opportunities of this way of doing agriculture is that we have all the ingredients for a great machine learning product, right? We have great observability. Every single thing that happens that we care about happens inside our walls and is either recorded or could be recorded if we realize we care about it. And everything is controlled. So we have the ability to say, this crop should get 13 minutes of light before 6 a.m., not 15. Or more realistically, this crop should get 22 hours instead of 21 hours of light. We have the ability to say it should be warm, it should have lots of nitrogen, it should have 17 days growing before it's transplanted, right? We got all the variables at our disposal. So we have all the observability, all the control, and we care about how productive the crops are, how much they yield, and how tasty and delicious and perfect they are from a consumer perspective. That is a high-dimensional search problem. And so one of our sort of main lines of work is to figure out how to make that an efficiently searchable space. So anything we can do to make our data world streamlined, make this sort of potentially sort of really deep complexity manageable to us and to the rest of our company, we benefit from really quickly. And so DBT helps us do a lot of that. One of the benefits of working in a cool physical business is that you get to put slides like this in no matter what you're talking about. So this is a picture of our farm in Kearney, New Jersey. You can see the verticality. So we're up about 50 feet, crop over crop over crop. And this goes for, like a Sam's Club warehouse sort of depth in that direction. Each of these units is our unit of analysis. So you can see sort of like this area here is 4 feet by 8 feet. And we're growing a crop there, and we have our sensing, control, scheduling, everything at that level. So we have many, many observable units all running in parallel. And so the question is, how do we manage all that? How do we build systems that let us both understand what's going on and do something about it? This is a icon-heavy view of sort of how we've put it all together. I was thinking after I made this, I probably could have illustrated this using the DBT logo fewer than 5 times. But if this is the show you're going to show up to, you might as well go for it. We use a lot of AWS things. So if you know all of your AWS logos, you don't need to read the captions. But the big picture here is that we have multiple data sources. S3 events like files being uploaded from our cameras, pictures of the crops. Our first-party applications saying things like this harvest was just completed or this crop was just entered into the system. And IoT saying this is the temperature reading, this is the light actuator setting, all of these things that are local to each crop area. they're all coming in over a message bus and being streamed into the warehouse with Kinesis. So we take, one thing that's interesting about this as a data engineering problem is that it is big in an agriculture world, not big in a media world, not even probably big in a online financial advisor world. And it's also very predictable. So we will not all of a sudden get 4 times as many plants on a day because we run a good commercial, right? We know exactly how big our farm is, and it's very easy to like, our graph of like events or messages per day is like incredibly stable, which makes my job really easy. We have a team of 6 in the data and AI world, and we don't have any data engineering specialization yet. And we've been able to do that basically leaning really heavily on AWS to just like take care of scale, and using dbt to like simplify. You know, I've never written, in a year and a half of managing a lot of databases, I've never written like a create statement yet. So that kind of like simplicity, both sort of like in this tooling and in this cloud stack, means that we do all this without really making it a like real engineering discipline yet. We'll probably need to before too long. Our Redshift world, which is our dbt world, has 5 schemas. And I will go into some more detail, but the basic idea is all the data shows up in load. We extract it incrementally with dbt into ingest. This gets us into tables that we can work with. Transform it into warehouse, into things we want to talk about. And then from warehouse, we go to report for all of our aggregates, all the things that we want to show people in reporting. Predict, this is the schema I'm going to talk the most about today, so I won't tell you anything else about that. Predict can feed back into warehouse if we want to take things that we predicted about the world and describe them in the context of our other main entities. And then this whole cycle is the part that I'm really proud about in terms of design and how low effort it is to participate in closing this loop. Predict is data, you can see is derived from the warehouse. You can do whatever you want with it here in a data science, building models, predicting things kind of way. All you have to do to participate in feeding back into the system is deploy an application that puts something on the message bus. So anything that takes warehouse data, predicts something, emits a message to SQS, which is super easy to do, then becomes sort of like primary system data that other things can build on top of. And so that's the piece that I'm gonna talk the most about. But that's how we sort of close this loop, doing very little in the way of like machine learning engineering, using mostly dbt. So a little bit more just in terms of like, this evolved over, well, first it evolved while I was the only person on the team, and I, you know, like drew this out and started building it and then crumpled it all up and threw it in the trash 4 times while I like looked at the dbt Slack about what other people were doing. But this is what we've pretty much settled on, and works pretty well and has covered our needs for a couple of years now. So the things that are special about ingest, it selects only from load. So the only ingest is not complicating itself with other pieces of the world. It's just this one incoming stream. There's literally one table. Every single message from the message bus ends up in a big table named load, and you can select from it whatever you want. Anything you want to know about the world, you select from load into ingest. All those models are incremental because this is our one table with a couple 100 million records, and it's all JSON payload. So you want to do this not every hour. So all these tables are incremental, which is pretty easy because they all sort of just append only, and you just process whatever's new every hour. You parse your JSON payloads. You store things type standardized, and you know, keeping only the things that you care about from that universe of things that are in the data. And we generally keep that modeled one-to-one with whatever the incoming sources are. So in ingest, the tables reflect, the models reflect sort of whatever anybody else modeled. So whether it's from one of our software services that's first party, or whether it's from like a third-party integration that's coming over the message bus, we don't try to add cleverness in this layer, right? We save that for the warehouse. So you move on to the warehouse, you select from ingest or from itself, or later from predict. It is a pretty standard star schema with dimensions and facts, and slowly changing dimensions, which we have quite a few of. And this is where we get to take our sort of authorship into our analytical world and say, this is what a crop is. This is what it means for a crop to be completed successfully. All of those sort of business definitions, but not business definitions in like a reporting kind of way, but in a what are our core concepts and what are our standardized ideas and how are they defined and where do we store all that logic one time. Predict is where we do our machine learning work. And again, that's what I'll go more into, but predict selects from the warehouse. So if you're gonna predict, for example, the mass of a crop that will be harvested next week, you're gonna wanna pull from the crops table. The crops table is in the warehouse. It's already been sort of cleaned and standardized, and that's the only place you should be looking for inputs. Contains observations and predictions. Models correspond one-to-one with projects. So if you're gonna predict a thing, crop harvest masses, you have a set of tables in the predict schema that are just for that purpose. And that's a key thing, that in the predict schema, you are not trying to meet generalized needs, right? You're not trying to be like the crops table that everybody needs. You're trying to be the crops table for the predicting crop mass project. And then we use some of those values, like the predicted mass of a crop, we pull those back into the warehouse. So in DM crops up in the warehouse, you've got the predicted mass so that you know how much arugula you're expecting next week, right where you're looking at all the other masses coming and going. And then finally, report. I think these three are probably pretty familiar to everybody, right? They're relatively common patterns. We didn't call one of ours base because that convention seemed to really gel right after I got everything set up. But report selects from warehouse or at rolling up other report schemas, aggregates by time period or whatever else your unit of interest is. And that's where all of the crazy logic about like, you know, what your weekdays are and all that crazy stuff, hopefully all gets defined exactly one time. And our sort of like goal is that 70% of the stuff of the queries written in mode look at the report schema. You shouldn't need to go and figure things out and calculate things. Of course, that's like an aspiration. You're curious about things and you want to report on things more quickly than you sort of formalize them into the report schema, but that should be how it plays out. And we basically have everything as either materialized tables or as view or as incremental, but that like in concept is basically just a bunch of views on top of warehouse tables. Again, just gives you another sort of sense of the space and density and how many crops you fit into a space like this. So the thing that I was excited to share with everybody here today was how we've used DBT to simplify the needs of someone trying to develop a machine learning model. So you're trying to figure out how to predict a valuable thing, say crop masses in our example. Your first goal or your first requirement is to get all of those predictive features and your outcome organized into something nice and tabular, right? And for predicting the mass of a crop, you might need to know what cultivar it is and how many days it's been growing and how intense the light was and whether you remember to water it, right? All of these things that are like reasonable, pretty straightforward, you would expect that to affect the outcome. But all of those are in all these different places. And so the question is, how do you bring all of those different features, some of which may already be sort of straightforward database columns in the warehouse, some of which you may need to do some processing that's very idiosyncratic or specific to your model idea. How do you bring all this together so that you can train that model and so that you can then deploy that model and have that running in production? And so as I sort of got familiar with this problem, you know, while I was at Betterment and then while I was setting things up at Bowery, this is kind of the common world of choices for solving that problem. So if you're a big tech company that does this all the time and you're a big deal, you just build a system that's for this, right? You build a tool set, a stack of tools for your machine learning team so that reused features, right? Concepts that you always use in training, sort of when those features are calculated in deployment stacks, all of those sort of like use cases for how I take an idea, right? I wish I could predict mass using these 5 things. How do I explore that and how do I deploy that? You just build tools that are specific to your ecosystem. And the other thing that's common to that solution is infrastructure teams that have like time and interest in building those things. Many of us, probably most of us, don't work at places where there's someone excited to build you like a machine learning training platform to do this work in. And so that is great and lovely and probably the best thing, but not an option for many of us. Maybe the other end of the spectrum are these solutions where you sort of deploy the notebook, right? Data scientists are used to working in a notebook. You query something, you you create new columns, you calculate new things. It all happens sort of linearly. You add a bunch of stuff, you're exploring, you get rid of a column, maybe you remember to run all the cells in order. And in the end, you get something that sort of starts with a connection to the database, does anything that you want it to do, and then produces some sort of output values, right? And that is your model. And that is absolutely functional. There's no overhead to this, right? Nobody has to learn any new tools. It is very native to the workflow that people are used to. But I do feel like no overhead has to be in quotes, because running a growing system of production services running on notebooks has some of the scaling and engineering risks and challenges that comes with sort of letting everyone, or building systems that depend on everyone using the tools that were designed for exploration and iteration. So that's a blessing and a curse. It's definitely quick to start up. One thing that I think is particularly limiting is the idiosyncratic solutions and a lack of reuse, right? That if I define something really valuable, some sort of second derivative of canopy area growth, and I do that in my notebook, and someone else has a related project, they probably can't conveniently use that code or use that column as a feature in their model, right? They could copy and paste your code from their notebook to your notebook, but they can't actually sort of structurally use that, which I think is a real drawback and a real benefit of something like DBT, where you're really trying to emphasize the dry expression of your data world. And then this third option is machine learning as a services. So you can absolutely take your whole CSV and upload it to AWS or to DataRobot, and they will solve these feature engineering problems for you and give you a deployable endpoint, right? The problem is, so one, you're going to be constantly moving your data from your first-party world into this third-party world in order to get answers back. And then, there's just sort of a long-term risk that you didn't get to make all the engineering decisions. And so as a result, you're limited in this or that capability or flexibility or the speed that you can offer predictions, or any of these other things that it feels really easy when you use someone else's tool to get out the door, and then you end up stuck in the limitations of that tool set. So I wanted some of the aspects of each, right? I wanted feature reuse, I wanted limited overhead, I wanted reliable implementation, and I wanted sort of just enough engineering rigor. I didn't want to have a team because I didn't have one, but I wanted to have those nice qualities without sort of burdening the system that was pretty new, and a lot of it the value still needed to be proven, right? You don't want to build a big stack before you've shown that this is even a valuable thing to predict or a valuable part of the system. So the predict schema in DBT solves these problems for us. And so here are the three rules of the predict schema, or really the three models that a model in our world has. Sorry, the use of the word model was really challenging for me in this talk. The three DBT models that accompany every machine learning model that we want to productionize. So observations, so each project has an observations, a predictions, and then an overall table. The observations table has exactly one record per observation that you could make a prediction about, whether the outcome value is known or not, right? So you have a lot of data that you can train on, a lot of records you can train on, as well as outcomes that are not yet determined that you want, that are sort of your predicted case, your cases to predict. You can imagine how easy it is in DBT to explore the world of extra features that you want to engineer, right? You just add a new column in DBT, which is the trailing 4-day light intensity, and now you've got that feature in your training set to work. And it works not just while you're working here in your laptop, right, and querying this table and having your training set in memory. It also works if your production service queries against that table. So you've got exactly one definition of that feature that's already in production, and you can use it in the training phase and in the deployed phase. Predictions is a table where you collect all of the answers that you have given to this prediction problem in production. So one record per prediction, but importantly, potentially more than one prediction per observation, right? Because you might run a model for a year or a week, depending on how often you get back to retraining. You retrain that model, you forecast, or you sort of backfill all of the predictions on old cases. You can have multiple predictions per observation in this table. And then it makes it really easy to compare the accuracy of these predictions over time by the model hash, right, which is one of the columns in that table, so that you can see sort of like what different models would have predicted for the same idea over time. And then this third DBT model is just the join of the obs and the preds, keeping only the most recent, or whatever your definition of the current official prediction is, so the model that you're considering the production master. And that's what you would query for people who want to know what you think is going to happen in the world. Right? So you have one place here. It's really easy to say, all right, we're moving over to model version 12. You just update how this M crop mass is defined, and then that is what all of your other reporting and anything downstream already points at. So now you know what you're expecting from each of those records. So that's sort of the design of what these tables give us. The value, which I may have already mentioned some of along the way, we get to reuse in observations while you're defining these features. You get to reuse the official definitions and all of the sort of any macro you develop to do any of these useful things. You get to reuse all of those throughout your machine learning world, which is a feature of like pretty fancy systems. The idea that somebody can define like a key business concept or a useful predictor, and that gets used in a bunch of different models. All of your training, validating, all of those machine learning workflow processes are just selecting subsets of that same table. And so you can do whatever sort of like cross-validation selection you want out of that table. And you're sort of always working on the same set of observation IDs. But that over time, right, when you're retraining, that observation set keeps growing and growing, right? Because you keep doing your business, more stuff because it's DBT just keeps showing up there every hour. And so the flow to retraining is really graceful. You just select from the same table, randomize however you did the first time, and you're good to go to update. Also, upstream data quality flows in. So anything you realized was wrong about your measurement of the canopy area at day 7, improvements to that upstream stuff in your data warehouse flows through because you've shared all that logic. Now that does mean that if you introduce some vision, you do fun machine learning stuff like this, why not take every opportunity to show it? So this is a video of arugula growing. You can see on the left, so on the right is our raw image of the arugula growing. On our left is the canopy area model. So this is a deep learning model that classifies every pixel as canopy or not canopy. You can see the red line here increasing, showing that the canopy is closing or closed about this date. And you can see here, these bounding boxes are indicating stressed arugula. And this yellow line here is showing like a severity score of arugula stress. And so over time, things were going great here, right? And the crop was growing. And then here's where you call the agriculturalists, right? And you say, this crop needs something from us. Ideally, in a little while, we will just automate that solution. But right now, it's great to notice this before we pull it down and it's time to send it to Whole Foods. So happy to take any questions about agriculture or DBT. Thanks.
John, did you have a question?
What's executing DBT for you guys?
We run in DBT Cloud.
Good plug. I have a second question while I have the mic. You talked about sort of reusing a lot of different feature generation methods. Is that stuff that's like tucked into macros or something like that? Like running sums and 4-day lookbacks and that sort of thing?
I mean, most of that stuff, we don't have that many things that are so idiosyncratic that they aren't already calculated in some upstream table, right? But if you do, if you end up with an idiosyncratic thing, you have it in the model that's specific to this machine learning project, and then you can reuse that. And if you are about to reuse it, then you should put it in a macro, and that's not like an out of flow use of the system.
Great talk. Most of my questions are plant related though. So what is the most consistent plant that you guys work with?
It's a good question. Currently, so there's sort of like a crop troublemaker of the week environment in our world. Our Siberian kale right now is really low variance. And that's actually something we talk about is, so yield is the thing that we are trying to maximize, the amount of product you get per space and time that it took to grow. And we look at the average yield, but our supply chain team can't actually sell the average yield, right? They have to sell like some percentile that, you know, carries them over every packing period. And so we have a concept called reliable yield that tries to capture sort of like, you should improve the mean, but the mean's not great if the variance remains huge. So we try to respect both of those.
Question? Yeah.
So it definitely is clear how DBT is useful for tabular data, but how is it that you process the image data or video data that you're working with?
True. This model didn't really use DBT that much. That's not true. This model refers to an observations table, which is all of the images of arugula, right? So the observations table still defines the set of records, which in this case, it comes from our F-images table, the set of records that are relevant for prediction in this model. And then every hour or every day when it runs, it looks for the set of observations that don't have predicted values, and that's how it runs. The actual model here is built in TensorFlow. But it's still, DBT is still intermediates, like what is the set of things that we can make predictions on, and how's our performance on that?
Any other questions?
What do you use to orchestrate, let's say, TensorFlow with DBT, or do we just assume asynchronous DBT's up to speed and we just kind of write back to the data warehouse whenever we get?
It's a great question, right? So our DBT world runs hourly, and for the majority of our history so far, that's been plenty. So our different machine learning services check hourly or whenever is good for them, predict on all the unpredicted cases, and it flows back through in the next hour. We are getting into a world now where we need things that are more timely. When our data products are integral to like real-time production systems. So you can imagine predicting canopy area. We estimate canopy area once an hour, and really we're interested in the trend over, you know, like the rate over a month, and so hourly is fine. For our services that are more real-time, we're actually priming those models and systems with an export from DBT, and then incrementally updating them from the message bus directly, which is nice because that AI application doesn't have to maintain state long-term, because you can always reprime it from the DBT view and then start updating from the real-time source. That answer? Yep. So all the models at the very least announce their predicted values to the bus. In some cases, they need to tell somebody directly right away also. But yeah, through the bus is sort of like the common interface for everything that we build.
Thanks. My question is around validating the pipeline. So obviously you're feeding back in multiple times over. You know, machine learning models specifically, like you mentioned, you have a bad feature, whatever, kind of causes some issues. How are you managing that specifically in the context of like all the AWS services that you're using? Or just in general?
The like engineering robustness or the like model predictive robustness?
I guess they're related, right? So how are you verifying that the sensor data is actually within whatever ranges you want, or like validating the input data that eventually becomes those features?
I mean, DBT tests is a big piece of believing what we have in the warehouse. So we have, I don't know, I think claiming test numbers is fun because it's a big number. We have, you know, like a couple thousand tests validating things that way. Obviously, the majority of those are not null. And so there's an opportunity to sort of like really test that things are not out of range. The question then is like, we've actually bifurcated things that we feel like are suspicious from things that we feel like are failures of our DBT logic. Because we were failing a lot of tests on things that didn't feel like true, but were not because we did anything wrong in the code, right? And so we've actually sort of taken things, and maybe DBT warnings would help us with that. We moved things that felt like likely sort of upstream data quality or system data quality problems into Slack alerts, still from DBT as their source, so that we can sort of like work on remedies to those without going into a failing state. So, I mean, I think the general process is every time something goes wrong, you write a test so that you would notice that automatically in the future. I don't have like that much of a grand, insight on how to always know. A lot of these things are really hard because there's not a right answer. We never get ground truth. And so if you're predicting whether arugula is unhappy, you don't find out for the cases that come out the door unless you do more annotation. And so that's like a real ongoing challenge that we need to keep, but we have to keep annotating, or we have to build something into our system to get more coded data over the long term.
How did you do that Slack alert thing? Because we have a similar issue with null values being due to operational issues and people not putting data in the system that we would expect. Where did you bifurcate that? How did you
It's in our warehouse repo. It is so the question was how do we do Slack alerting? I actually asked, I think, in the DBT Slack, what are people doing for this? And I was like, I don't think we should build this ourselves. And then we built it ourselves. And it wasn't that hard, actually. It went much quicker and has worked more robustly than I thought. It is just a Python script that runs every hour, runs a query against the warehouse, and if there are any records, it posts the records to Slack.
So it's like separately documented.
It is. Yep.
Cool. I think that's it.
Thank you very much.
Okay.
Everybody.
Yeah, thank you so much, Sam. Okay. I am a massive over caterer, so we ordered some more pizza. So please eat some more pizza, grab another drink, and say hi and stick around for as long as we can. Thank you so much for coming out tonight.